So we're going to talk about momentum and impulse. So far in class, what we've looked at is just the equation that you see right here in front of you, where you have your initial momentum and your final momentum. And the stuff in between right here is the sum of all the impulses acting on the object. So these are those instantaneous rather than sustained forces that act on something like during an explosion or a collision. And you add all those up, and whatever that change is gives you your final momentum, as we see over here. Now, we're about to take a step from one dimension, which is what this represents, into two or more dimensions and have things collide. And it's actually pretty easy for us to do that, because all we really need to do is we need to do this in the x direction, like this, and then all we need to do is make a duplicate line where we end up using the same type thing, but in the y direction. So now we'll have all these forces in the y direction, because momentum, if you recall, is a vector. And we could do this, for z as well, but we're not going to really need to worry about z in this class. So you can have that in the x direction and the y direction, because momentum and impulse are both vectors. And just like we've been breaking velocity up in class, we're now going to break up our forces here and continue to break up our velocities. And then we treat the problem much the same way. Kind of like when we were dealing with kinematics. Same song, second verse. Just twice as much work, because we have to break it up into these separate components of x direction, y direction, and if need be, a z direction. So that's really all there is to it. In doing this, we can look at an example here in just a second, where we'll look at the momentum of an object and maybe talk a little bit about the forces acting on it. So I'm going to take a second, clear the screen, and we'll check that out. Okay, so I wrote this out. Some object, I'm trying to keep this very generic. So object A travels at 10 meters per second at an angle of 40 degrees. It has a mass of 15 kilograms. It experiences a force of 500 newtons at 20 degrees. So what happens? So essentially what we have is we have this object, and it's traveling along this direction. It has its velocity at 10 meters per second and has an angle of 40 degrees, like so. And then something happens. We don't really know what, and there's just some type of a collision. But it experiences a force of 500 newtons at 20 degrees, and so that force, is going to be maybe like so. And we can say that's 500 newtons at 20 degrees. And I kind of need to give it some time. We'll say that this lasts for t equals 2 seconds. So after 2 seconds, the force will go away, but we need to give it a time so that there can be an impulse. So that's our problem, that's our setup. We can assume that, maybe it gets a burst of speed. If it's like a rocket, turns on its engine, something like that. Don't know. Doesn't really matter. We just have this object, has a momentum because it's moving, and then it experiences a force, and what happens next. So let's look at this by writing out our x direction, and we will have our x direction has cosine for the velocity there. And then the only force we're really concerned with is the force that I said was there, so we'll have a force acting over the time. But we need to make sure we're going to use phi, to use this separate angle here, to identify that. So we'll have that force, and then that's going to result in our final velocity. So we'll have v2 cosine, and then I'm going to call this theta 2 because after we have that collision, chances are we're going to be in a separate direction. And then we'll do the same thing in the y direction. Give myself a little bit more room. And like that. Not cosine. And so it's important now, I'm going to use green to kind of highlight this. Green to talk about the things we know. We know the mass, the velocity, and the angle. This is all known. It's going to be a numerical quantity. This is also a numerical quantity because we know all those angles. We know the time of the collision. We know the force of the collision, or the impulse, whatever's causing this. We still know the mass at the very end. That's not going to change for us. The two things that are going to change for us, and I'll highlight them here in blue, is v2 and theta 2. But luckily we have two equations and two unknowns. So at this point you have some options. You can go and you can plug in and say, okay, I'm gonna find out by substitution, identify v2, solve for v2, and then plug it in up here and then calculate theta. I prefer not to do that because we have technology. In fact, that's why you're watching this, it's technology. Instead, what we're going to do is we're going to use Wolfram Alpha. You won't see me do it, but I'll go plug all this into Wolfram Alpha, and then I'll come back and we will have an answer. And I'll continue to use blue for that. So what we'll be solving for is v2 and theta 2. Okay, so our velocity looks like it's going to be about 71.4, maybe 71.3 meters per second. And then our angle then is 36.6 degrees. So that sustained force actually put a whole lot of speed into this, right? And it actually decreased our angle slightly from the 40 degrees, and it's to be expected because we're coming in at a lower angle and pushing it at that direction. And so we were able to correct course a little bit down to 36.6 degrees. Velocity jumped way up there. So that's an example of this. Please rewatch it. We'll be using it for collisions in class primarily, but I wanted you to be able to see that it's pretty much the same thing. We just do it in two directions now. So until next time, stay physicsy.